In 1901, divers recovered a corroded bronze block from a shipwreck. Inside were 30 interlocking gears, a 2,100-year-old mechanical computer. We still cannot replicate all of its functions using only the tools we know they possessed. The location is the bottom of the Aegean Sea, 60 meters deep, near the Greek island of Antikythera. Radiocarbon dating places the ship around 100 BC. For almost 2 millennia, salt water and sand consumed everything perishable. The wood, the hemp rope, the leather, all dissolved into the seabed. Only the bronze remained, and even then, transformed into a green, brittle crust. When sponge divers brought this block to the surface in 1901, it looked like an unremarkable piece of limestone. It sat in a box at the National Archaeological Museum of Athens for months. No one noticed what was inside. The machine had vanished under the corrosion, but the mechanical result remained. What researchers found upon scraping away the marine deposits defied our entire understanding of ancient engineering. There was no record of anything like it at any other archaeological site. No gears, no precision mechanisms, no calculating devices, just stone ruins and simple tools. The Antikythera mechanism was not an agricultural tool or a weapon. It was an astronomical computing instrument built to model the universe. And the immediate question was, how did a culture that used copper chisels and fiber ropes produce gears less than 2 millimeters thick? The machine is gone. The corroded bronze still holds the memory. Let's look at the numbers. The Antikythera mechanism measured approximately 34 centimeters wide by 18 centimeters high, with the thickness of a pocket watch. Inside this compact space were at least 30 interlocking bronze gears, organized in layers. The largest gear has 223 teeth. The smallest gear has only 38 teeth. The cutting tolerance of the teeth on these gears is 0.1 millimeters. That is 1/10 of a millimeter. To cut bronze teeth with this precision, the cutting tool cannot vibrate. The operational clearance between the teeth of 2 meshing gears is approximately 0.3 millimeters. If the clearance were any larger, the mechanism would jam or skip teeth, losing the synchronization of the celestial cycles. If it were any smaller, friction would generate heat and rapid wear. The Antikythera mechanism tracked the Metonic cycle, which synchronizes the solar and lunar calendars every 19 years. It tracked the Saros cycle, which predicts eclipses every 18 years, 11 days, and 8 hours. The precision of these eclipse predictions was within a matter of hours, not days. The mechanism used differential gears, a mechanical principle that does not appear in any other historical record until the 14th century in Europe. Differential gears allow rotations to be subtracted or added simultaneously. In the case of Antikythera, the differential gear calculated the variation of the lunar orbit, modeling the elliptical motion of the moon around the Earth. This requires 2 gears to rotate in opposite directions while feeding a central 3rd gear. The mechanism also featured a date indicator, an Egyptian calendar, and tracked the cycle of the Olympic Games, marking the passage of 4 years. Each of these cycles required a specific gear ratio. To represent the 19-year cycle, the builders used 2 gears with a ratio of 38 to 19, simplified to 2 to 1. But for the Saros cycle, the ratio was 223 to 19. This required a combination of multiple gears in a complex gear train, with intermediate gears transmitting the force. The gears were not just toothed wheels. They had shafts mounted on parallel bronze plates supported by cylindrical pivots that needed to be perfectly aligned. If a shaft were off-center by half a millimeter, friction would destroy the mechanism within a few months of daily use. The Antikythera mechanism was not a crude prototype. It was a finished product of precision engineering, operating with a level of tolerance we would not see again until Swiss watchmaking 1,400 years later.
The gears also had pins mounted on their centers, which moved pointers along circular scales engraved on the front face and back plates. These pointers tracked the positions of the 5 planets known at the time. The precision required in these engravings was the same as that of the gears. The first serious modern reconstruction attempt began with Michael Wright, a researcher at the London Science Museum in association with Alan Bromley from the University of Sydney. Wright used linear X-ray tomography in the 90s to map the internal structure of the corroded block. The initial problem was that bronze, after millennia submerged, undergoes a process of crystallization and expansion. The internal gears were pushed against each other, deforming the teeth and forming a solid, distorted mass. Wright had to count the gear teeth through low-resolution X-ray images where the metal contours overlapped, creating confusing shadows. He built a functional mechanical replica based on his tooth count and the shaft positions he could identify. Wright's replication attempt was a partial success. His mechanism tracked the sun and moon with reasonable accuracy, fulfilling the basic function of the Metonic cycle. The gears meshed, and the pointers moved continuously. But Wright could not reliably integrate the lunar differential gear into his first model. The friction in the opposing gear system was too high for the layout he proposed. The force required to turn the mechanism manually caused the smaller gears to skip teeth, breaking the synchronization of the Saros cycle. Wright revised his model over several years, adjusting the gear ratios, shaft positions, and spacing between the plates. He demonstrated that the mechanical principle of the differential gear worked, but his replica revealed a fundamental practical problem. The original mechanism required a level of fine-tuning in the shaft bearings and internal lubrication that modern reconstruction could not replicate with available machining techniques. The ancient bronze seemed to have a composition, perhaps with a higher tin content, that resisted wear in a way modern bronze does not. Wright's attempt proved the machine was real and functional, but it did not explain how the ancients kept it running without friction destroying the system in a few years. Wright's replica also faced a challenge with the gear articulation pins. In the original mechanism, the pins connecting the gears to the linking arms had a diameter of only 1.5 millimeters. In the replica, these pins tended to bend under rotational stress, especially when the operator forced the crank to advance the calendar quickly. This suggests the original mechanism was not designed to be cranked rapidly, but rather advanced slowly and deliberately, one day at a time. Wright's model remained the best physical reconstruction for almost a decade, establishing the gear count and basic mechanics, but leaving open the question of how precision was maintained under continuous operation. The second reconstruction attempt came in 2005 with a team led by Tony Freeth, a researcher at Cardiff University, and Mike Edmonds from the University of Bristol. They used high-resolution computed tomography with microfocus technology developed by X-Tech Systems, capable of generating three-dimensional images of the internal structure of the corroded bronze with 0.1 millimeter detail. This technology revealed something Wright could not see: microscopic inscriptions on the internal and external surfaces of the gears, which functioned as a user's manual built into the mechanism itself. Freeth and his team were able to read inscriptions that were hidden inside the fragments, folded by centuries of marine pressure and covered in deposits. The inscriptions listed the celestial cycles and planetary positions the mechanism tracked, confirming the function of each shaft. Freeth's team proposed a new reconstruction model, including the gears that tracked the 5 known planets: Mercury, Venus, Mars, Jupiter, and Saturn. The replication attempt, based on Freeth's data, was an advancement over Wright's model. The arrangement of the planetary gears used a system of eccentric shafts and sliding pins to model the speed variations of the planets in the sky, a concept that approaches Ptolemy's epicyclic model, centuries before Ptolemy formulated his theory. However, the replica based on Freeth's model also faced severe mechanical problems. The planetary gears, especially those modeling the retrograde motion of Mars, required even more rigorous tolerances than the lunar gears. The sliding pin representing the orbit of Mars tended to jam at the points of greatest angular velocity variation, where the planet appears to reverse its direction in the sky. Freeth's team published their results in the journal Nature in 2006 and 2021, detailing the complete cosmology of the mechanism. But the physical replica still cannot operate continuously without interruptions. Freeth's model explains what the mechanism did, but it does not resolve how the ancients manufactured the components so they wouldn't jam under the frictional forces generated by 30 gears turning simultaneously in such a small space. The lunar differential gear, which Wright had already identified, remained the biggest point of failure in modern replicas. The wear on the teeth of modern bronze gears is visible after only a few hundred rotations. The original mechanism would have to withstand thousands of rotations over its operational life, maintaining a precision of tenths of a millimeter. Here is the central problem. The Antikythera mechanism is not a mystery of purpose. We know what it did. We know how it did it in terms of mechanical principles. We even know the names of the cycles it tracked, engraved on the bronze. What we do not know is how it was built to function in practice. The gap is not conceptual, it is mechanical. The lunar differential gear requires 2 gears to rotate in opposite directions while feeding a third. In a 34-centimeter space, the shafts of these gears are mere millimeters apart. The bearings supporting these shafts must absorb lateral force without generating excessive friction. In modern watchmaking, we use synthetic rubies as bearings to reduce friction to near zero. The builders of Antikythera did not have synthetic rubies. They had bronze, iron, and wood. Their solution to the friction problem is unknown. No modern replica has been able to reproduce the mechanism without friction destroying the precision in a short time. This suggests the ancients had a technique for polishing shafts and holes, or perhaps a method of lubrication that left no trace in the archaeological record. The second problem is the manufacture of the gears. Cutting 223 teeth into a bronze gear with a 0.1 millimeter tolerance requires a cutting tool harder than the bronze. The tool was likely tempered iron, but tempered iron does not survive in the archaeological record, especially in a marine environment. Iron oxidizes and disappears completely. The tools that created the Antikythera mechanism likely dissolved in the Aegean Sea centuries ago, along with the wooden structure that housed the mechanism. The third issue is the historical void. The Antikythera mechanism dates to around 100 BC. The next mechanism of comparable complexity, with differential gears and astronomical gear trains, appears in Giovanni da Dondi's astronomical clock in Padua around 1364. That is a 1400-year gap. In no other field of engineering do we see such a long hiatus between a technology and its next appearance. In architecture, we see continuous progression. In metallurgy, we see continuous progression.
But in precision mechanics, there is an absolute void. No intermediate mechanism has been found. No isolated gear from a later century has surfaced in excavations. Either the Antikythera mechanism was a unique object built by a solitary genius whose knowledge died with him, or there was an entire tradition of precision mechanism manufacturing that simply left no traces. The second option is more likely. The quality of the mechanism suggests an established tradition. The presence of manual inscriptions suggests it was not a display object, but a working tool. But if there was a tradition, where are the other mechanisms? The probable answer is that they were made of bronze. Bronze was valuable. In the late Roman Empire and throughout the Middle Ages, bronze was melted down to make coins, weapons, and bells.
A complex mechanism like Antikythera would have been a perfect deposit of recyclable metal. The mechanisms that could have filled the 1400-year gap were likely melted down. What wasn't melted rotted. The wooden structures decomposed, the iron tools oxidized. Only stones and buildings remained, which do not require gears to be built. The machine is gone. The Antikythera bronze survived by accident because a ship sank before anyone could melt it down. And even then, it barely survived. Corrosion nearly erased the gears. If the ship had sunk in more oxygenated water, nothing would remain but a green stain on the seabed. The lingering question is not what the mechanism did. The question is, how did a civilization that produced this machine produce nothing else like it that survived? The engineering required to create the Antikythera mechanism demands workshops, specialized tools, mathematicians to calculate the gear ratios, and artisans to cut the teeth. This is not the work of one man alone. This is infrastructure, and that infrastructure vanished completely. The specific mechanical gap remains: how the bronze bearings operated without excessive wear, and how the differential gears maintained synchronization under load. Without resolving this, the modern reconstruction remains incomplete. The reconstruction of the Antikythera mechanism used high-resolution computed tomography, three-dimensional digital models, and physical replicas in modern bronze. It achieved a complete understanding of the mechanism's function, the celestial cycles it tracked, and the gear ratios required for each cycle. The reconstruction proved that the mechanical principle works. The original, however, achieved the same function with a mechanical precision and wear resistance that modern replicas cannot sustain for more than a few hundred rotations. The gap is twofold. First, the specific mechanical problem of friction in the bronze bearings and the jamming of the differential gears under continuous load. Modern replicas fail where the original succeeded. Second, the historical void of 1400 years without mechanisms of comparable complexity in the archaeological record. The Antikythera mechanism is not an isolated anomaly in human thought. It is an anomaly in the archaeological record. The mathematics required to calculate the gear ratios of the Saros cycle and the Metonic cycle were known in Babylon centuries before the dating of the mechanism. The mechanics of simple gears, such as watermills and traction devices, existed in the Hellenistic world. What makes Antikythera unique is the convergence of this mathematics with manufacturing precision on a miniaturized scale. The question is not whether the ancients were smart enough to conceive the mechanism. They were. The question is how they turned the concept into a physical device that did not jam after a month of use. The answer likely involves surface finishing techniques that leave no visible trace. Cold polishing, heat treatment of the bronze, or the use of organic lubricants that decomposed completely. We know the Greeks used olive oil and animal tallow as lubricants in other applications. But the viscosity of these lubricants does not seem sufficient to keep a 30-component gear train operating with tolerances of tenths of a millimeter. The infrastructure that produced the Antikythera mechanism was made of perishable materials. The workbenches, the wooden lathes used to polish the shafts, the iron drills used to cut the teeth, the measuring instruments used to verify the tolerances. All of this decomposed or was melted down. The tradition of precision mechanism manufacturing likely existed for centuries in the Hellenistic world, fueled by the demand of elites who wanted to predict eclipses and track the movements of planetary gods. But this tradition was interrupted. The fall of the Hellenistic world, the rise of Rome, and the economic changes of late antiquity transformed the bronze of complex mechanisms into coins and armor. The practical knowledge of how to build these machines was lost, not because it was impossible, but because there was no longer enough economic demand to sustain the specialized workshops. Precision engineering is expensive. It requires time, rare materials, and highly trained artisans. When the economy supporting these artisans collapsed, the tradition died. The Antikythera mechanism is the sole survivor because a ship sank before the bronze could be recycled. It is a fossil of an extinct tradition, not the only member of a species that never existed. The machine is dead. The corroded bronze still remembers what it calculated, but the secrets of how it operated without destroying itself were lost along with the workshops that created it. The modern reconstruction of the Antikythera mechanism is a reminder of what we lost. We can digitize the bronze, we can count the teeth, we can 3D print the components, but when we assemble the replica and turn the crank, the gears jam, friction wins. The original mechanism operated for years, perhaps decades, without jamming. The difference between the replica and the original is the distance between what we know and what we understand. We know what they built. We do not yet understand how they built it to last. The next puzzle we are going to investigate is not a computer, but a drilling machine. In the Valley of the Kings in Egypt, there are holes in granite 30 centimeters deep and only 5 centimeters in diameter, cut with a precision that copper chisels cannot explain. The internal walls of these holes show marks of perfect spiral rotation, indicating that a cylindrical drill rotated at a constant speed while advancing into the stone. The machine that drilled this granite left the mechanical signature of a precision lathe, but the Egyptians were not supposed to have precision lathes. The next puzzle we are opening is the Valley of the Kings drilling probe. If you want to see how wood, rope, and copper could have spun a drill through solid granite with perfect rotation marks, subscribe to the channel. The next video investigates the machine behind the impossible holes in Egypt.